Welcome, my name is Cenk Gündoğan, and with my colleagues Christian Amsüss, Thomas Schmidt and Matthias Wählisch, we explore in this paper a RESTful data-centric Web of Things for IP-based group communication scenarios. Common Web of Things networks have cloud services that connect via gateways to IoT devices using low-power and lossy wireless solutions. Many use cases such as wildfire detection in forests and the correct propagation of collective firmware binaries require a reliable and efficient group communication. Iterated unicasting is a naive approach which imposes critical network stress. IP multicast is the traditional solution in the internet, but is challenging in IoT networks. It's unreliable and struggles in lossy regimes. Many IoT link layers map multicast to broadcast, and transport layer security complicates IP multicast. Previously, we did investigate on a CoAP-based data-centric Web of Things deployment option and observed reliable content retrievals with reduced network utilization. In this paper, we follow up with the question whether we can extend our work with a reliable and secure multiparty communication. In the remainder, I will briefly recap the data-centric Web of Things and describe our extensions to make it multiparty aware. I will present our testbed experiments and will then conclude with takeaways and future work. CoAP is the IETF application protocol for constrained networks. It's based on the REST paradigm, typically built on UDP, and implements an end-to-end reliability. The research community around information-centric networks explores the use of named data networking for the IoT. NDN operates on the network layer and uses hop-by-hop reliability. Research indicates that information-centric properties have promising benefits in low-power environments. Stateful and hopwise forwarding coupled with in-network caching and request aggregations shorten request paths and reduce link traversals on retransmissions. Content object security enables an end-to-end protection with a reduced session management complexity. We replicated these properties for a CoAP-based data-centric Web of Things using standard protocol elements and very small modifications. A CoAP proxy on each hop along a path allows for the same stateful forwarding, request aggregation, and hopwise caching as NDN, while OSCORE enables security on a content object level. But standard OSCORE introduces a strong message binding, which prevents aggregations between iterated requests and also renders the caching layer completely unusable. These problems negate all former benefits in multiparty scenarios, which leads us to our multiparty extensions. We modified two aspects of our deployment to enable group communication. First, we make OSCORE messages cacheable by using the role of a virtual client that members can assume. Requests from this virtual client produce identical cache keys independent of the actual origin. Second, we modify the proxy forwarding to aggregate requests per cache key. Same requests from different origins produce only one upstream message, and returning responses fan out to all interested endpoints. We performed all experiments on the IoT Lab testbed and the IoT operating system Riot. We looked at the use case where identical actuators periodically request instructions from a single server in a multi-hop network. We compared four protocol options. The first one deploys the typical end-to-end OSCORE setup. Then we use our former data-centric deployment with CoAP proxies on each single hop. In the deterministic deployment, we use the multi-party customizations, and then we look at NDN. All setups perform 3 retransmissions following a 2-second timeout. We measured the arrival time of instructions at each client. Client 1 is closest to the server, client 5 is in the middle, and client 9 has the longest path. We observed more than 60% of requests to finish in the milliseconds range for the end-to-end OSCORE setup on client 1. The staircase in the seconds range denotes retransmissions. Client 5 and 9 are not able to recover the losses, and success rates fall to roughly 40%. The proxy deployment has slightly better success rates because retransmissions benefit from hopwise caches. NDN greatly outperforms the previous setups because it fully leverages the caching and stateful forwarding. When we add multiparty extensions to the proxy deployment, then we see reduced latencies for requests and elevated success rates very close to NDN even for client 9. We highlight 2 takeaways. First, it is possible to build a data-centric Web of Things with multiparty support using CoAP standard protocol elements. And second, stateful forwarding and hopwise caching also improve the reliability of IP-based group communication. In our future work, we will look at the discoverability of multi-destination routes and the translation of CoAP unicast to CoAP multicast at CoAP proxies. Thank you for listening. Our code is publicly available at this GitHub URL. All implementations are part of the free and open source IoT operating system, Riot.